So far we have learned how to use the Lagrangian and Hamiltonian formalism to solve optimal control problems. So this is the optimal control problem that we have been dealing with, including 3 elements. The first element is the dynamic models. So it's written in this differential equation: x dot is equal to some function f. And the performance index is given in this form, including the terminal cost function s and the integration cost. And the boundary conditions, the initial condition is at x0 and the final condition is free. So this is a general form of optimal control problem that we have been dealing with. And so far we learned 2 different methods. One is called a Lagrangian formalism, and the other one is a Hamiltonian formalism. Hamiltonian formalism is also called a Pontryagin principle. So let's look at a Lagrangian formalism. So Lagrangian formalism defined the Lagrangian function L is equal to v plus these 2 terms together, that is ds dt. ds dt can be decomposed into 2 terms. One is partial s, partial x, times x dot plus partial s, partial t, plus lambda transpose times g. The g describes the constraint, which is also the dynamics. G is equal to f minus x dot. So this is how we define the Lagrangian function. And optimal control is solved by letting partial L, partial U is equal to 0. You can solve for the optimal control. The 2 differential equations we have, one is partial L over partial x minus d dt partial L partial x dot is equal to 0. And the other one is partial L partial lambda is equal to 0. And this is the same as its dynamics. The boundary condition is given in this uniform form, and depends on whether TF is fixed or not, and whether XF is fixed or not. You have different combinations. And later on, we define a Hamiltonian. The Hamiltonian is defined as v plus lambda transpose times f. And we wrote L in terms of the Hamiltonian. Then we get all the results related to Hamiltonian formalism. And the optimal control is obtained by letting partial h, partial u is equal to 0. And you can find the optimal control. And this solution to this gives you the relationship between the optimal control and the co-states. Then you submit that to the Hamiltonian so that you get an optimal Hamiltonian. And that optimal Hamiltonian will be a function of x dot lambda. The 2 differential equations, the first one is x dot is equal to partial h partial lambda. The second one is lambda dot is equal to negative partial h partial x. And the boundary condition is in this form. And I have 2 terms. One term is related to delta TF, and the other term is related to delta XF. Depends on the different boundary conditions that you are given. You may have different equations that allow you to solve for the constants. These 2 pages summarize how we use Lagrangian formalism and Hamiltonian formalism to solve optimal control problems. So now we're going to use what we learned to look at a more complex problem. We're going to use both of 2 methods to solve them, and we are also going to use MATLAB to solve them as well. This is a problem we're going to use as an example. Find an optimal control for this plant. This is a second order system. x1 dot is equal to x2, and x2 dot is equal to something else. And the performance index J includes the terminal cost function. And there is also the v function. V is everything inside this integration, so that is half times x1 squared plus 2x2 squared plus 4u squared. The initial conditions is given, and the additional conditions are given in these different conditions. So we are going to look at all these different conditions, how we're going to handle them. So the first method is the Lagrangian formalism. We need to first define the Lagrangian. So let's copy the Lagrangian. We have a v is defined everything inside here, so that is half times this, and a function s is equal to this. But remember, function s is a function of x, is not a function of xtf, right? Because we need to put that into the integration so that we use the former result to derive some results. S is a function of x1t plus half f22 x2t minus 2 squared. So this is our S function. And f and x dot, this is a function g. So f is given here. So f have two terms. One is x2t, the other one is this negative 2x1 plus 3u. The second step, the optimal control is obtained by partial u. Let me copy that so that I can save a little bit time to. So this will give us optimal control. Let's see what that is. This is the L function, partial L, partial u, and the first term is the function of u. So that is a 2u squared. You take a partial derivative of that with respect to u, you get a 4u. So we can see that S is a function of x, it's not a function of u. So partial this term over partial u, that is equal to 0. And the next, partial L over partial u, here f function is a function of u. So it's better for us to write it out if you cannot see in the answer right away. The first term is lambda 1 times x2, it's not a function of u. The second term is lambda 2 times this. We take a derivative of that with respect to u, so that it will give us 3 lambda 2. That is equal to 0. So solving this will give us the optimal control in terms of the co-state lambda. That is equal to negative 3 over 4 lambda 2. And we can also find the differential equations. And we have two differential equations. One is this Euler-Lagrangian equation, and the other one is the partial L over partial lambda. So we have two differential equations. Because we have two states, one is x1, the other one is x2, so in total we're going to get 4 differential equations. So let's see what is the first differential equation. Partial L over partial x1 minus d dt partial L partial x1 dot is equal to 0. So we want to see what that is. Partial L over partial x1. We have x1 here, so you take a partial derivative of that. That will give us x1. So let's write this out. So this term over here is equal to partial s of partial x1, partial s, partial x1, that'll give us f11. So if we look at the problem, the f11 there are constants. No matter which condition, there are constants. So we just use f11 there, and take this term with respect to x1. So we have a 2 times x1 minus 4. That 2 will be cancelled with the former half. So that is x1 minus 4. What is the partial s over partial x2? Partial s over partial x2, we have a f22 times x2 minus 2. So the transpose of that times x1 dot and x2 dot plus partial s, partial t. Is s a function of t? No. That's it. So that will give us the first element times this first element here, x1 dot, plus the second term times x2 dot. Now we can continue. Partial L over partial x1, we take a derivative of this term with respect to x1. What do we have? So this is x1, so that we have a f11 times x1 dot. And anything else? Partial L, is this a function of x1? We need to find out. Let's write this out as well. Don't have enough space. Let me just write it over here. And we have 2 lambdas, right? So you have lambda 1, lambda 2. Transpose times f minus x dot. So f function x2, the first equation is x2 minus x1 dot. And the second equation is negative 2x1 plus 3u minus x2 dot. And that will become lambda 1 times this plus lambda 2 times this. Great. Then we put everything together. Because L is composed of 3 terms, so we're going to do the partial derivative of all the 3 terms with respect to x1. Let's see what we get. The first term over here, take a partial derivative of that with respect to x1, we get a x1. The second term over here, we take partial derivative of this with respect to x1, we get a f11 times x1 dot. This is over here. The third term, we take a partial derivative of this with respect to x1, we have a negative 2 lambda, right? So we have these 3 terms. And next, this is partial L over partial x1 dot. The first term is not a function of x1 dot. That's why it's 0. The second term is a function of x1 dot. And we take a partial derivative of that. This will give us the coefficient f11 x1 minus 4. And the next function over here, we take a partial derivative of this with respect to x1, that give us a negative lambda 1. And that's it. We get the first differential equation, partial L partial x minus d dt partial L partial x dot is equal to 0. We applied this equation to x1. So we get this. We can simplify this a little bit more. So that will give us, this term will be cancelled with this term. And that will leave us x1 minus 2 lambda 2 minus 2 lambda 2. This is a minus lambda 1, and you take a derivative of that, which will become plus lambda 1 dot. That is equal to 0. Good, you find one differential equation. So we can further write it as lambda 1 dot is equal to negative x1 plus 2 lambda 2. And the next equation is about x2. We're going to do the same thing, but apply to x2, and let's see what we have. The first term, partial L over partial x2. We have 3 terms, so we're going to do it 3 times, right? The first term, partial this with respect to x2, we get 2x2. And the second term, take a partial derivative of this term with respect to x2, that will give us f22 times x2 dot. The third term, partial this with respect to x2, that will give us lambda 1, and then d dt. Inside over here, we need to find a partial L partial x2 dot. Let's see what we have. The first term is not a function of x2. Perfect, that's 0. The second term is a function of x2 dot. That will give us this, f22 x2 minus 2. And the third term, take partial derivative of this with respect to x2 dot. That will give us minus lambda 2. We have minus lambda 2. That is equal to 0. We can simplify this a little bit more. The derivative of this term, f22 x2 dot, will be cancelled with this term, right? So that will leave us 2x2 plus lambda 1, and this is a minus d dt lambda 2 dot. So there's another minus sign, so that will become positive. So that's a plus lambda 2 dot is equal to 0. We can write it in terms of the differential equation. Lambda 2 dot is equal to negative 2x2 minus lambda 1. All right, we find another equation. We got the 2 differential equations from the Euler Lagrangian equation. The next equation is the co-state equation. So this basically gives us the differential equations. We can just copy the differential equations directly. Now we have 4 differential equations. We can try to solve these differential equations. We'll use MATLAB to do it. So we provide you a template. You can just customize the template to help you to solve the differential equations. Let's just save as example 3. In this example, we minimize the performance index, and this is performance index 0.5 times f11 times x1 minus 4 square plus 0.5 f22 times x2 minus 2 square. It's half the integration from 0 to tf. 0.5 times x1 square plus 2x2 square plus 4u square. The dynamic equation dx1 is equal to x2, and dx2 is equal to negative 2x1 plus 3u. So this is the dynamics. And the boundary conditions, the first boundary condition is a fixed final condition. And here f11 is equal to 0, f22 is equal to 0, and tf is equal to 2, x2 is equal to 4, 6. We do know there is another initial condition, x0 is equal to 1, 2. Right? So x1, 0 is equal to 1, and x2, 0 is equal to 2. This initial condition will apply to all these different cases, right? So right now we only look at case 1. There are additional cases. The second case, we have f11 is equal to 3, and the f22 is equal to 5, and the xtf is equal to 4, 6, and the tf is free. The case 3 is a free final state condition. f11 is equal to f22 is equal to 0, and x12 is free, and x22 is equal to 6. Come back to our differential equations. So we first define some symbols. The first one is x1 as a function of t, and x2 as a function of t, and lambda 1 as a function of t, and lambda 2 as a function of t, and ut. So these are the symbols that we have, right? And the differential equations, the first differential equation we have is here. Lambda 1 dot is equal to negative x1 plus 2 lambda 2. Let's just write it out. Lambda 1 dot is written as a differential lambda 1 with respect to time t, that is equal to negative x1 plus 2 lambda. So we'll write it as negative x1 plus 2 lambda. So this is the first differential equation. The second differential equation is here. Lambda 2 dot is equal to negative 2x2 minus x1. The third differential equation is x1 dot is equal to x2. So we write it as diff x1 dot is equal to x2. And the last equation is the differential of x2 with respect to time t is equal to negative 2 times x1 plus 3u. And what is our u? We already found the optimal control u in terms of lambda, right? U is equal to that. So let's write it here. We already found our optimal control, and this optimal control is given as a u star. So I'm not going to write a star all over the places, but you know that that is optimal control. U should be u star. It's equal to negative 3 over 4 times lambda 2 star. So here we're going to replace u by that. So we just copy u times negative 3 over 4 times lambda 2. Alright, that's our differential equation. Let's see what we get. So I'm going to comment out all the others. I just want to solve for these differential equations for now. Let's see what s dot x1 is. That is x1. So let's see s dot lambda 1. So that is s dot lambda 1. We solved these differential equations. Next, we're going to apply the boundary conditions so that we can solve these constants in this differential equation. And we're going to look at 4 different boundary conditions: case 1, case 2, case 3, and case 4. Here, we're going to write the 4 different cases. Step 3, apply boundary conditions. And here we have 4 different cases. we can use the case statement. So it's called a switch. So this is how you write a switch case. Switch expression and the case. And here you can select a different choice. We can start with the choice 1. So in choice 1, and if this is first case, and we'll do something. And if it's the second case, we can do something else. And if it's the third case, we'll do something. And the last case is case 4. We can use otherwise. So in case 1, we're going to dealing with the condition of f11 is equal to 0. Let's see how we find the boundary conditions. So in this problem, f11 is equal to 0, f22 is equal to 0. And if we look at our differential equations, and then now the differential equation have f11 and f22. So actually that's really nice. All these differential equations will be always like that. It's not affected by f11 and f22. So tf is equal to 2. We also have this overall boundary condition, right? Let's copy this as well. So we just need to submit the t as 0 to x1. We can do it like what we did before. And if we want to put a u there, we can do this as well. So let's define the symbols. We can define the symbol t0 and tf. And here t0 is equal to 0. And tf is equal to 2. Then we're going to write the equations. The equations are defined as these boundary conditions. So let's copy everything, including the plots. I'm going to copy it and put it over here. So let's look at how we revise that. So the first equation, we have a sub f dot x1 at a time t0 is equal to 1. That is given. Perfect. And the second equation, we're going to substitute s dot x2 at a time t0 is equal to 2. And the third condition, subs s dot x1 at a time tf is equal to 4. And last equation is subs s dot x2 at a tf is equal to 6. Let's solve these equations and see what we can get. So I already choose the choice 1, so it will only run this part of the code, and all the other part the code will not run. So we find ss dot c1 is that, and ss dot c2 is equal to that. It's an expression. It's not approximated by using a value yet, but we can convert that to a value if we want to convert s dot c1 to a value. Oh, sorry, I wrote it wrong. So this ss dot c1, that long expression is 2.1954. Let's come back to this. And we'll tell the system C1 is my C1, C2 is my C2, and C3 is my C3, and C4 is my C4. I find that I'm going to plot the result. So this will allow me to plot the result. And if you want software to help you to organize the code automatically, you can use the the combinational key of a control and I. If you select that portion, it will organize that portion. If you select the whole code, it will organize the whole code for you. So it's control I, and then it will organize the code for me. So since I use dt and t all the time, so t0 and tf is here. I define that dt is equal to 0.1, and since I'm going to plot it from t0 to tf, and here I want to solve the value of s dot x1 and s dot u, but s dot u is not defined, remember. So we didn't put a u there. So we can define s dot u. So we can define s dot u is equal to this, right? It's related to lambda 2. We need to use the s dot lambda 2 because lambda 2 is put in this structure of s. x1 is equal to subs s dot x1, and x2 is equal to subs dot x2, and u that is equal to double subs s dot u. So that will give us the result, and we'll plot state x1. Let's plot x1 and x2 together. tx1, we'll plot tx2 as well. Did we get everything? So x1, x2, x1, x2, tu. Okay, so this is the first choice. This represents the first problem, right? Let's plot that. And click wrong. It takes a while for the calculation. So these are our states. If you want to know which one is which, it's better to put a legend. Let's add the legend. Here, yeah. Here we can put a legend. And this is the plot that we are working on. We'll just do it here. Oh, I do not need the bracket. Yeah, so this is how we put the legend. Let's correct that in the code as well. We have two plots. The legend should also have two of them. One is x1, the other one is x2. It will tell us which one is which. So we solve the differential equations, and step 4, apply boundary conditions. The boundary conditions that we have, x0 is equal to 1, 2, and x2 is equal to 4, 6. We solved this equation. Now we find optimal control and the states. Now we can put the results here. Let's grab the results. So this is the optimal states. This is optimal control. Let's look at the results. So we want to control the robot. Initially, the state is at 1, 2. So x1 is equal to 1, right? And x2 is equal to 2. So that started from the right initial position. Then eventually we wanted it to reach 4, 6. And it should get to 4 and 6, right? So it means the boundary condition is properly applied. And at the same time, this trajectory is the optimal control that will guarantee that this will get there with the performance index optimized. So the performance index for the first problem is this, but with f11 is equal to 0, f22 is equal to 0. Alright, let's look at how we solve the problem by using Hamiltonian. So we're going to solve the same problem by using Hamiltonian formalism, and Hamiltonian formalism is also called a Pontryagin principle. So the approach is very similar. So the first step is to define the Hamiltonian function. The Hamiltonian function is defined as a v. Let me just copy this. And we also need to know what is v and what is that term. V is the same, is everything inside of the integration, right? So v is the same. F function is everything on the right hand side. So we can write the second term. So we're going to do the same thing. We're going to match the color. So this is a v. Let me select a different color. So this is our v. Lambda transpose times f. I'm going to select a different color. Lambda is a vector that will give us lambda 1 times x2 plus lambda 2 times that. x2, x1, and u, they are all functions of the time t. So the second step is to find optimal control. We'll use a partial h, partial u is equal to 0. That's how we find optimal control, right? Partial h over partial u. The first term is a function of u, right? This is a 2u squared, and we do partial derivative of that. That will give us a 4u. And the second term, we have a function of u, which is a 3 lambda 2. We take a partial derivative of that. That gives us 3 lambda 2. That is equal to 0. We can find the relationship between u and lambda 2. And we also notice that this is exactly the same as what we got from the Lagrangian method here, right? So we can find a u star is equal to negative 3 over 4 lambda star. The next step is to find an optimal Hamiltonian. The optimal Hamiltonian is to replace u by lambda so that the Hamiltonian will be a function of lambda and the states. The Hamiltonian is equal to this with u replaced by negative 3 over 4 lambda 2. So that will be half x1 squared plus 2x2 squared plus 4u squared. U squared will be represented by 3 over 4. So that is a 9 over 4 lambda 2 squared. The second term, lambda transpose times that, we're going to do the same thing, replace u by negative 3 over 4 lambda 2. And we also know they are all at an optimum, right? So you need to write optimum. So now we have to find this. The next step is to find the differential equations. The differential equations are the state equation and also the costate of our lambda dot, right? The state equation, even if you don't solve this, we already know that the state equation is related to the dynamics. That's our dynamics, but with u being replaced by negative 3 over 4 lambda 2. So let's get that. Step 4, differential equations. So if you want to refer to what we summarized here before, you can copy these two equations. One is about the state, the other one is about the lambda. Then we'll write the differential equations and see what we have. The first differential equation is about the dynamics, right? But we have a u replaced by lambda 2 already, right? So remember, this u is replaced. And at the same time, lambda dot is equal to partial h, partial x. So let's write that out. Lambda 1 dot. And it's a function of time t. I'm not going to write that, just to make it a little bit shorter. So let's get rid of t. Lambda 1 dot is equal to negative partial h, partial x1. And h star is already defined, h star here. So this is a partial h here. H is also the h star because we use the optimum, right? So it'll be this will become partial h, partial x1. The first term will give us x1. and this term no h1, and there is another h1 term which is a negative 2 lambda. Since we have a negative sign in front of it, so that it becomes plus 2 lambda 2. The last equation is about a lambda 2 dot. Lambda 2 dot will be equal to negative partial h partial x2. Let's see what that is. So this is the first term over here that will give us x2. The second term, we do not have a x2 with a negative sign. Don't forget this is a negative sign. Let's compare the equations with what we got from Lagrangian formalism. So in the Lagrangian formalism, we got lambda 1 dot is equal to that, lambda 1 dot, and also lambda 2 dot is equal to that. The first two equations are the same. The second equation, lambda 1 dot is equal to negative x1 plus 2 lambda 2, that's the same. The next equation is different. Lambda 2 dot is equal to x2.
Lambda 1 x2 on the previous page. I think we forgot about that. Yeah, where the on top, where the lambda transpose f of xt u of t. Yeah, that one.
Oh, I missed the one term. I was wondering what's happening. We missed something. Thank you. This optimal Hamiltonian. Just now we missed the first term. I was wondering what's happening. So this is optimal as well. The optimal Hamiltonian. Let me copy and put it over here. The second differential equation, lambda 2 dot is equal to negative partial h partial x2. That will give us, this is a negative x2, right? And we also have another term over here that is a negative lambda 1.
Professor, shouldn't it be a negative 2x2?
Oh yes, you're right. So this is negative 2x2. Now let's look at the differential equations. This is what we have. And we can go to the Lagrangian formalism and we can take a look. So these are the two differential equations. This equation, lambda 2 dot is equal to negative 2x2 minus lambda 1, right? And the previous equation about lambda 1 dot is also the same. So we have the same differential equation, and we have the same boundary conditions. Let me copy the boundary conditions over. Then we'll be able to solve the problem. Let's solve it by using MATLAB. So we already know the differential equations are the same, so we should get the same result. The only difference is that we find optimal Hamiltonian first, and this u that is replaced by negative 3 over 4 lambda 2. Then we can solve this problem, then eventually we should get the same results. Since the differential equations are exactly the same and the boundary conditions are the same, I'm going to just use this solved result and put it over here. Alright, so we finished the first case.